Thanks for right. So why the LHS every term? So what is LHS? LHS is this term, summation of M. T is over all trees. Can someone say why every term in LHS will have at least two variables of degree 1? This follows from a simple property of trees that we have discussed.
Every tree has at least 2 leaves.
Good. So since every tree has at least 2 leaves, which so we observe two basic property and clearly, okay, let's make property 3, which is really trivial. Option 3, each term in LHS, RHS is divisible by x1 to x. That's kind of obvious because by definition RH is divisible by x1 to xn, and LHS is also divisible by x1 to xn, because if you take every monomial for a tree, these variables are present, right? x1 to xn. So that's it. So these are the 3 properties. So now let's get back to the proof again. Okay, so when we say two polynomials are equal, obviously two polynomials are equal if and only if the coefficients of all the monomials are same in them, right? That means the task that we have at hand, we really want to prove that all the monomials in this two polynomial are of same coefficient, right? Okay. So let's see how we prove that. So, okay. So one thing to note. So look at, there are lots of monomial in the left hand side and right hand side, right? So look at a monomial, for example, where x1 appears of degree 1. Okay. And these monomials, so let me just explain to you. So doesn't matter. Look at either you LHS or RHS. So look at all the monomials of degree where x1 has degree 1. So they look like x1 times something plus x1 times something. The something is also like a product, right? And so you group, suppose I group all the monomials that where x1 appears together, and then I take x1 common, write these things. So this will be also some monomial, right, of the smaller degree. So such a term I give it a name. I call it polynomial pure. This is also a polynomial that I call P1. Similarly, one can define polynomial P2, P3. Right? Right. Let's make another observation. So look at RHS or LHS. We do not know whether they are equal or not. We are going to prove that, but you can look at either RHS or LHS. How can we extract the polynomial which is the coefficient? Okay, so these polynomials I call this polynomial P1. For simplicity, I call it is the coefficient polynomial for x1. Is that notion of the coefficient polynomial is clear? Or anybody has any doubt? Ask me if you have any doubt. If you do not ask, then I'll go ahead. How we suppose I give you the LHS polynomial or RHS polynomial. Let's say RHS polynomial, and I tell you how we can extract the polynomial which is the coefficients of x1. What shall we do? Right, this is nothing particular about our polynomial. This strategy is true for any polynomial. So a very simple way to do that: divide. Suppose I am working with RHS. Argument is similar for LHS, of course. Divide RHS by x1 and then substitute x1 equal to 0. Can everybody see why that gives the coefficient, which is the coefficient polynomial? Why by this process I get the coefficient polynomial of x1? If you divide by x1, which term survives? The term that contains either x1 once or x1 many times, right? They survive. Okay, so if you are confused, are you sure that what I am saying? Is it okay?
Yes, sir, it's clear.
Okay, fine.
So, when we substitute 0, then in the terms where x1 appears multiple times, those will vanish.
Those will vanish. So, and only the terms where x1 appeared once, they survive after dividing by x1 because there is nothing is substituted by x1 equal to 0. Right?
So we want them to vanish.
Sorry?
We want those terms to vanish where x1 appears multiple.
I want to maintain the terms which has x1 exactly once.
Okay.
That's the definition of P1. See, P1 is the term where x1 happens to be exactly once. Whoever asked, is it clear to you?
Yes, it's okay.
So now look at RHS. RHS is X1, and this process, of course, it is nothing to do with the RHS or LHS. It is true for both, right? So if you look at X1 to Xn times X1 plus X2 plus Xn power n minus 2, then if you divide by X1 and then substitute X1 equal to 0, what is your P1? P1 will be X2 to Xn times X2 plus Xn power n minus 2. And this is nothing special about X1. You can do this process for X1 to Xn. Yeah. Now we make a very simple observation. To prove LHS equal to RHS, it's enough to prove that the coefficient polynomials for X1, Xn are same in LHS and RHS. That means we are supposed to prove just two polynomials are same, LHS and RHS. We are giving a recipe instead of proving it directly by probing into every such monomial. It will be enough if we just argue that collect the coefficient polynomial of the variable x1 from both sides, coefficient polynomial of the variable x2 from both sides, and so on, and prove that they are individually equal. That will suffice. If you can convince me, then I will be convinced, oh, then these two polynomials must be same. So why? Is the question is clear? The claim that it's trying to make. Is the claim is clear, or anybody has any doubt?
Yes, sir.
Okay, good. So let's. So Milan, can you tell me whether you think why you think it is true or false?
So I think I have a doubt, sir. This is
Yes,
Akratin here.
yes,
So
yes.
there'll be some linear terms of x1 and some linear term of x2,
Hmm.
and we'll be counting them twice, no?
What do you mean by counting them twice?
So for example, the sum
First,
of all coefficients for
first, let me just remind
when
you that.
x1 is linear.
Let me just remind you that every term has x1 to xn. So don't get confused on that. Now tell me your question. What confuses you? Or what is your question?
I think I understand now. Yes.
Actually, if you just sit back, relax, and think it for a moment, it's very easy. And the argument is the following. Suppose LHS is not equal to RHS. Then there exists a monomial M which has coefficient C1 in LHS. So maybe C1 could be 5 and C2 in RHS. Maybe C2 could be 7, such that C1 is not equal to 7. But any such monomial M must contain a variable xi for some I such that the degree of xi equal to 1, right? However, we have assumed that what? Can somebody complete it?
That's
That's
coefficient polynomials of for
Exactly.
all I are equal. So
Right.
this should not be happening.
Very good. Yes. However, we have assumed that the coefficient polynomials for xi are the same in LHS. That's a contradiction. Very good. Okay, so once we realize this, we have a simpler goal in hand. That, by the way, technically, when I write this, I wrote last time also. Technically, when I write, I can write from n greater than equal to 2. N equal to 2 is trivial to check because that is just x1, x2, and both sides are same. So we have a refined goal in our hand, like we have to prove only this much. Instead of thinking all the polynomial individually, we will just think about that. So because of the claim, let us try to prove that the coefficient polynomial without loss of generality for xn. This argument is same, obviously, for all the variable are the same. I just write the proof for xn, proof for any other polynomials are exactly same. Okay, so this proof we'll use induction. Okay, so the base case of Kelly's identity is n equal to 2, and by IH induction hypothesis has shown that it is true for trees over 1 to n minus 1. In other words, that is, we have C of n minus 1, x1 to xn minus 1 equal to product of x1, x2, xn minus 1 times x1 plus x2 blah 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 xn minus 1, right? Okay. Now, what is the coefficient polynomial? It's very simple, of xn in RHS. That is, we already computed for x1 the same argument. It is x1 to xn minus 1 times x1 plus xn minus power n minus 1. We have divided by xn and substituted by xn equal to 0. So now look at LHS. How do you compute the coefficient polynomial of xn? That's also very simple. That means those polynomials xn must appear like a leaf, right? And then there is a tree on top of it. So xn must be a leaf. So the leaf can be connected with either x1 or x2 or xn minus 1. That means what are the terms that give you xn as degree 1? So the total term will be xn, and then xn must be accompanied with one of them. That is x1 plus x2 plus xn minus 1 times, this is like the tree on n minus 1 vertices, for which the function I know that by the definition is x1 to x n minus 1. Is that argument? This is the crux of the observation. Is the observation clear? If I collect the term that contains xn of degree 1 from the LHS, this is what we get. Can everybody understand it, or there is any doubt? Let's think about it. How can xn come with a degree 1? It must come from the term where it's a leaf. And when it is leaf, it can be attached to one of these variables, x1 to xn minus 1. And regardless of whatever it attached to it, on top, there are all possibility of the trees of x1 to xn minus 1. Any doubt? Ask question if you have any doubt. No doubt? That's good. Hence, the coefficient polynomial for xn is equal to x1 plus x2. This is a beautiful proof that by Kelly. Cn minus 1. Now use induction hypothesis. But this is equal to x1 plus x2 plus xn minus 1. Substitute by induction hypothesis. This is x1 to xn minus 1 times x1 plus xn minus 1 power n minus 3, which is equal to x1 to xn minus 1, x1 plus xn minus 1 power n minus 2. See, we have found it. In that RHS, the coefficient polynomial of xn, and in the LHS, the coefficient polynomial of xn's are exactly same. The argument is symmetric for all the other variables. Argument is symmetric for any other. It is amazing how 1889 Kelly proved this kind of argument when today it is known as polynomial methods in combinatorics. Scroll over. Now, from where the Kelly's theorem is immediate, right? You just plug xi equal to all 1 and you get what you want. Any question, then ask me. Any doubt?
Once we had label the vertex, like last day you said that we just write like we can represent any tree uniquely with x1, x2, like a sequence of xi, right?
Right.
So total where the sum of the degrees should be 2n minus should be 2n minus 2. No, yeah, 2n minus 2 because of the number of vertices.
But this encoding is not unique. This encoding is not unique. That Aditi, that example she gave last time, it showed that this
if we take the permutation, like if we don't commute the elements first, we just don't commute, then it will be unique, right? We take x1, x2, x1, x3 as different from x1, x1, x2, x3. We don't commute at first.
So are you trying to give a different proof of Kelly's theorem? There are multiple proofs possible. Yeah, there could be other.
Yeah, then counting this. So basically, every like counting all the trees will be basically counting all this some of the monomials, which I'm assuming first they don't commute, and then each monomial has a degree of 2n minus 2, and x1 must every xi should belong should appear at least once in that monomial because all the vertices.
I cannot hear you. It's too noisy.
Yes, so
but I understand that you are trying to give some other alternative proof. There are 6 proofs known for Kelly's theorem. Yeah.
No, I'm just checking if that is correct. Like it is one liner from there, but I don't know like if that is correct.
But could you count it finally? I cannot understand all of your argument. This is online and I'm just hearing you with some noise.
Yes, it's okay. Should I repeat once?
Or you maybe write it. That's the best thing. You may write and maybe try to calculate.
Comment, okay. Okay.
So that is better.
Okay.
Think properly, because if you just orally say some proof in a very sketchy manner, it may be hard to follow because we are not having any blackboard. You are also not writing. Orally, it's very difficult. But it is possible that someone find another proof. There are lots of proof available for Kelly's theorem, and most of the proofs are combinatorial. And this is a particularly one algebraic. But every proof, if it is too simple, be careful that there is a catch in your argument. I mean, all the known proofs have some intricacy. It's not a trivial statement. Yeah. If you just manage it by 2 lines of counting, then you doubt your argument. Because every known proof of Kelly's theorem historically is somewhat tricky. It is not absolutely like a cakewalk. Yeah, since you are not writing, you are only saying it orally, I cannot clearly understand what your strategy is, but it may be correct. But if it is too simple, just verify it carefully. The reason this proof is important is that this proof generalizes to many things in combinatorics, and one of those things is matrix tree theorem. That not before mid-sem, but after mid-sem, I will probably try to teach. That's another great theorem proved by Kirchhoff's. The same Kirchhoff's for which you have studied probably Kirchhoff's law in physics. So there is a generalization of this theorem to matrix theorem. A very important theorem called matrix theorem builds on these ideas. Okay, so let's make a few points. The advantage of polynomial methods over combinatorial proof is that it's a very symbolic proof. So nothing can go wrong in it. Combinatorial proof, typically the way this Kelly's theorem, you have to set up a nice bijection and you have to be very careful in arguing. It's very good to know this. I encourage you to go back and read different proofs of Kelly's theorem, maybe from Wikipedia or from other books. But also remember this algebraic, which is particularly nice. And particularly since you are in CMI, you should know some algebra. Okay, so now the theorem follows by putting xi equal to 1. So C1, 1, 1 equal to each monomial will give you 1, and here x1, x2, xn, the product is 1, and 1 plus 1 plus 1, that will give n power n minus 2. Right. Just give me a moment. Okay. So, few corollary. So remember the notion of rooted tree. That's a simple notion. If I give you a tree on 1 to n vertex, then a rooted tree means one of the node you fix as root. You can choose any node you want. So rooted tree means one of the nodes. I just give it a special status, nothing else. One of the nodes. We can give a special status. What we call as root. So corollary 1 is that number of rooted trees on 1 to n is how many? Anybody? Total number of trees is n power n minus 2, and for every possible tree you can make any vertex like root. So there is n choice. So n times n power n minus 2, which is n power n minus 2. This is the number of rooted trees on n vertex. Corollary 2. So what is the number of forest?
So we can use generating functions.
Say it again.
Generating functions.
There are
We can use. So we can use generating functions. So
generating. Yeah, you can do, but then you keep on repeating this kind of idea. So because I have given you a strong theorem in hand, you can use this theorem and argue it in a very crisp way, instead of again going into a big. Yes, you can do it, but we can do it much more easily once we have this great tool in our head, Kelly's theorem.
2 to the power n to the power n minus 2.
Say it again.
2 to the power n to the power n minus 2.
2 to the power n to the power. No, that's not correct.
Can we do
What
something
is
like
the-
add an extra node which is connected
correct.
to all forests, so you can just it's the number of trees on n plus 1 things and deleting one node,
Right.
a fixed
Take-
one.
Take any additional vertex, say n plus 1. So now consider a forest that has T1, T2, TL possibly. These are the trees. Now you can associate a tree on n plus 1 vertex with respect to that forest. Right? Also, given any tree on plus 1. Take the children of n plus 1, and that defines a forest. Clear? That's what
So
Lawrence.
what is the definition of a forest? Can you repeat?
Forest is a collection of trees, disjoint trees. Yeah. Hence, the number of forests on N is in bijection with number of trees. So the number is n plus 1 power n plus 1 minus 2 by Kelly square. Is it clear? Okay, so next week is the mid-sem. So did you fix any tutorials with the TS? Or is there a communication between you and TS?
We had a tutorial last Sunday.
Okay, so no, that we requested the TS that if you have to discuss the that assignment solutions or any particular topic in combinatorics and this newer portion of graph theory, if it is not clear, then you can request tutorials. But it is up to you. If you want, then they will conduct because it's online, right? Otherwise, in the institute we always conduct, but since it's online, it's happening on request. So if you have any problem, then you can ask them. So the exam, this will be like 60% multiple choice question and 40% subjective question. I think, I'm not sure, but most likely there will be a kind of a tick mark facility in Moodle where you can select for the multiple choice.
Sir, I have a doubt in the last thing you proved, sir.
Sorry.
The last bijection you showed,
Hmm.
the number of forests in n vertices has a bijection is a one-to-one correspondence with the number of trees in with n plus one vertices.
Hmm.
So shouldn't it be? I mean, the bijection shouldn't it be between the number of forests in m vertices and the number of rooted trees in n plus one vertices?
Not rooted trees, because for any vertex you can make n plus 1, you can unofficially think it like root and collect its children. That defines a forest.
So what I was thinking was among the n plus one. So let's take a rooted tree in n plus one vertices. One of them will be the special status vertex, and all the children will like branch. All the different branches will be assigned as a tree, and that will give us a forest in n vertices. And the converse is already true.
So I guess you are saying the same thing by in a different way. I am thinking like you can take any tree and then I can think like n plus 1 is like a root and collect its children. That defines a forest. Is that what you are saying also? I guess so.
Yes, I think we are saying the same thing. So you can take one of the n plus one vertices, any one of them. So we have n plus one choices for that, and we get n plus one
No.
sets
I
of.
think you are making a mistake. If you run the choices for n plus 1, then it will be a problem. Then somewhere in the forest that n plus 1 also enter in its tree, in its children. You should not give the choice and make it complicated. That's why I took any trees on n plus 1 vertex and think that n plus 1 like a root and collected its children.
Okay, so I understand. Yeah.
Sir,
Yes.
so could you repeat what this thing? I don't understand Pratim's question.
Apathy was probably, if I don't know that I have also understood. So if I understood, you was probably asking like, why don't you take all rooted trees on n plus 1 vertices and then try to construct forest? But the technical problem is that then there will be something which is root other than n plus 1, and then n plus 1 go and get mixed with 1 to n, and that I don't want in my forest. My forest does not contain n plus 1.
Yes, sir.
So this was a much easier. Maybe he was trying to say the same thing, and but could
So
not
in fact, my answer is like almost the same except for a factor of n plus one. So
That's
according to
because
my
you have,
logic, the answer is n plus one to
yeah,
the power n. So I'm
that's
kind
because
of
you have,
trying
yeah,
to.
yeah, that's because you have given that additional n plus 1 factor by making it rooted.
Right, right.
That's the reason. Oh, sorry, I was telling something about the exam. So yeah, so this MCQ you have to mark probably like there is some tick mark facility and uh, and for the other part which is subjective, uh, so which way you can submit. So it will be some kind of fixed time you can write, and you have to probably scan it by a mobile or laptop and make a PDF file and upload in the Moodle. Is that what you are doing in other courses also for the real-time exams?
Yes, sir.
Okay. So anybody has any problem in at home scanning like these, or not a good mobile in hand, which you cannot, you don't have. If anybody is there who does not have a scanning facility, let me know.
So also, like you had previously said, there would be a take-home component. Is that not there anymore?
Take home. Is Ramya is there? 1 minute.
Yes, I'm here.
Yeah. So, did you say anything about take home for mixing?
Yeah, this descriptive part, I think we mentioned that it could be a take home, but yeah, now we have decided that maybe at least for the midsem, it will be descriptive. Like you have to write during the exam. Maybe end sem, I'm not sure. End sem, we can make it take home.
But we can allow you good amount of time. It need not to be like a absolutely pressure cooker kind of system, because we understand that this scanning and all these things will take additional time, right? So it will be given like this usual 40 marks, whatever time you get in a classroom exam, you will be getting considerably more than that, I suppose.
The time mentioned is 9:30 to 12. So
But that we can adjust.
yeah, there'll be buffer.
Yeah, so that there will be buffer, and we will be. We will
Of
not.
course, I think MCQ will be fixed time because it will be on the Moodle. You can time that session. For the descriptive thing, you can take some more time.
Right. And any of you has exam just following that 12:30 time, the same day, other subject?
No, sir. I think there was just one which they're rescheduling.
Okay. So maybe that in the buffer we'll change it to like 2 o'clock. Is that fine? That roughly like 1 or 1.5 hour, and you can have this scanning and all such things done. I'm fine. So okay, I think today maybe this next class is exam, so I will not take new topic because up to this exam, yeah.
I tried to write that on the comment thing I was talking.
Sure. You have written it?
Yeah, the second one. Yeah. That's right.
Okay, thank you for the information.
Thank you. Anybody wants to know anything about the exam, because we are not meeting you before that, please let me know, because we are not, probably I'm not in favor of starting a new topic now because it is not in the part of exam. We can do it after the next week. I think we have enough material.
Sir, just to confirm, could I write on a tablet and send